Now I'm recording. All right, thank you. Okay, here's problem set number 5. We have this heat engine that has an efficiency of 25%, and it has a power output of 900 kilowatts. We have an equation for efficiency that we've talked about in the past. The efficiency is equal to the work output divided by the heat input. And it tells us that we want to calculate the fuel flow rate, the amount of fuel going into the combustion chamber in kilograms per second, given that the fuel is wood and it has an energy content of 15 megajoules per kilogram. All right, so our first clue is that it tells us the thermal efficiency here. And we have an equation for thermal efficiency. And it also tells us what the steady power output is. So this would be the work output. And the only thing left in this equation to solve for would be the heat input. So we need to solve for the heat input, and then maybe we can convert that into a fuel flow rate since we know how much energy per kilogram the fuel has. All right, so that's what we're going to do. I did have a reminder here to myself, but I hadn't looked at that page yet. So thank you for reminding me before I got to that point. All right, so here is our equation for efficiency. It's the work output divided by the heat input. And we know what the efficiency is. It's 25% or 0.25. And the work output is 900 kilowatts. So the only thing left to solve for in this equation is the heat input. So we can do that by multiplying both sides times Q in, and then dividing both sides by 0.25. And that tells us that our heat input is 900 kilowatts divided by 0.25, which is 3,600 kilowatts. And I want to get this into megawatts because in the problem, we are given the energy content in megajoules per kilogram. So I can easily convert megajoules per second to megawatts and vice versa. So I want to get this value into megawatts because that'll make it easier to do some conversion. So that's easy. I just divide by 1,000 kilowatts and my kilowatts cancels out. So I get 3.6 megawatts. And now you have to maybe stare at this for a minute and you have to recognize that, oh, a megawatt is just a megajoule per second. And we've talked about that before. You know that a joule per second is a watt. So it's not too much of a stretch to say that a megajoule per second is equal to a megawatt. So 3.6 megawatts is just 3.6 megajoules per second. And we know how much energy is in 1 kilogram of this fuel. So all we have to do here is convert the megajoules to kilograms because it's asked for in kilograms per second. So all we have to do is this conversion right here where we have 3.6 megajoules per second. We know that's our energy input. That's Q in. We just need to convert that into kilograms per second. And we can do that by knowing the energy content of the fuel. So the fuel is 15 megajoules per kilogram. So our megajoules cancel out. And the units we're left with are kilograms per second, which is exactly what we want. So it's 0.24 kilograms per second. So about every, I like to think about this in my head, about every 4 seconds, we need to be throwing in a log of wood that's about 1 kilogram. All right, so that seems kind of reasonable, right? I mean, if this is a power plant with 900 kilowatts output, that seems kind of reasonable that we should be throwing a log into the combustion chamber, whatever is happening up here, about every 4 seconds. So that seems reasonable. Okay, number 2 is we are supposed to calculate the maximum possible efficiency. What is that? Well, that is the Carnot efficiency. That's the upper limit on the efficiency that you can ever get if your whole system is operating perfectly in an ideal manner. All right, so this is the Carnot efficiency, in an ideal manner. It's ideal, it's frictionless, and it's a heat engine. So the only thing that's really kind of tricky about this is you have to remember to convert these to Kelvin. So you need to take 145 degrees Celsius and add 273 to get the temperature in Kelvin, and the same thing with all of these other values. And after that, it's really straightforward. You just plug them into the Carnot efficiency equation, 1 minus T low divided by T high, or you can think of it as 1 minus T cold divided by T hot. Either way, it means the same thing. So we just need to convert all of our temperatures into Kelvin. So in part A, we convert 145 degrees Celsius to Kelvin, and we convert 23 degrees Celsius to Kelvin, and then we plug in the numbers in Kelvin, and we get 0.29 or 29% for part A. And then in part B, you notice all we did is we increased T hot. We kept T cold the same, so we just increased T hot. So we took 250 plus 273 to get 523 Kelvin, and then we plug in those numbers, and now we can see just by increasing T hot, we bumped up our maximum theoretical efficiency from 29% to 43%. And then from part B to part C, the only thing we did was we decreased T cold from 23 degrees Celsius to 0 degrees Celsius. So that remains the same as that. And T cold is now 0 plus 273, so we get 273 Kelvin. And we plug that in and we get 0.48 or 48% efficiency. So here, from part B to part C, all we did was decrease T cold. And by doing that, we increased our maximum theoretical efficiency from 43% up to 48%. All right, there's a few notes here. I think I've said this before, but generally speaking, from a practical perspective, think about operating a power plant. It's usually a lot easier to increase T hot. To make the boiler hotter is usually logistically easier than by decreasing T cold. It's just more difficult. It's more challenging to get that cold fluid reservoir just logistically. You got to refrigerate it, or you got to move your plant up to the Arctic Circle, or something like that. So it's usually more challenging to do this. But we try by reducing the pressure and use air ejectors to operate at a vacuum in the condenser. All right, so the point here is that the maximum efficiency that you can get in a heat engine is entirely dependent upon the temperatures that you're operating at, and specifically the delta T, the difference between the temperatures between the hot and the cold reservoirs. All right, that's problem set number 5. Any questions? Oh, here, let me stop recording.